Welcome back. Now I would like to talk to you about how we can prompt FDS to record specific types of data. Very similar to experiments, we need to define before we run the simulation which specific data types we would like to record. If we forget something, we need to rerun the simulation and record the specific quantity. FDS comes with many options to record data. For example, there are slices in which you can record gas phase data across a domain. There's also the option to record boundary data, for example if you're interested in the surface temperature of a wall. For now, the focus is here on devices. The recording devices can be of different shapes, for example like points or areas or volumes. In SmokeView, the default visualization of the devices is as green spheres. The size of the representation can be changed by hitting J. You can see here on the right hand side that the green spheres are getting larger when I'm hitting J. If you are hitting Shift plus J, the devices are shrinking again. This is only affecting the visual representation. This has no effect on the device itself. Sometimes it is just nice to have the option to increase the devices, because in complicated simulation setups it may not be so easy to see where the devices are located. For now, all the devices are shown as spheres. But as I said before, we can have, for example, devices that record information across a volume. We can now prompt SmokeView to show us the outline of the space that is taken into account for the specific devices. Inside the SmokeView window, simply right-click somewhere to open the dialog box. Then you can navigate through Show and Hide, Devices, and Show XB. Now with the black outline, we can see which spaces the individual devices are taking into account. The green spheres are located at their respective centers. It is important to note that in FDS, devices are not only used for recording. For example, there are smoke detectors and sprinklers, which are also considered a device in FDS. As you can see here, they are even getting their own visual representation in SmokeView. On the top left, you see a representation for a smoke detector, and on the top right, you see a sprinkler head. For now, I'm looking into the recording devices, and specifically, I would like to record gas phase temperatures along the center line above the burner. From the FDS User's Guide, 2 chapters are important for recording devices. The first would be Chapter 18, Devices and Control Logic. The next chapter would be 22, Output. Towards the end of Chapter 22, in Section 22.12, an overview is provided over the different gas phase quantities that can be recorded in FDS. They are summarized in Table 22.4. In the first column, the quantities are listed. This quantity is the information that needs to be provided in the FDS input file so that FDS knows which information to record. The next column provides a brief explanation about the given quantity. This is then followed by a column that gives you the unit in which the information is recorded. The last column gives an overview over the different file types. These are explained in the first paragraph of section 22.12. The capital D indicates that the data can be recorded via devices, capital I can use isosurfaces, P plot 3D files, and S the slices. As an example, let's have a look at this line here. The quantity is the temperature and it is recorded in degrees Celsius. The file types that are available is all 4. In the explanation, a link is provided to section 22.10.8 to give a better explanation about the quantity temperature. Let's now start to set up a device to record gas phase temperatures. The device name list is written as a DEVC, short for device. First, we start with giving the device a label. In this case, I've chosen temperature_1 or temp_1. Now the device needs to be positioned inside the domain. For now, I want to focus on points, so I can use the XYZ parameter and provide the 3 coordinates. To position the device in the center above the burner, I set the X and Y components to 0 and the Z component to 9 cm. With this, the device should be located in the second cell above the burner surface. Now a quantity needs to be provided. The quantity is provided as a string from the table that we were talking about earlier. When we run now the simulation, FDS produces a file that is labeled with the character ID _DEVC for the devices. I've just loaded this DEVC file into the Jupyter notebook that I'm using for the data analysis. Here's a brief overview over the content. In the first column in the CSV file, we get the time, and in the second column, the temperature that has been recorded. The temperature starts at 20 degrees Celsius. This is the default setting in FDS. Then we can plot here the temperature over the simulation time. We see there is some ramp up in the beginning, and then at some point it stays fairly constant, which you would expect because the gas burner is set to a constant heat release rate. In the end, I would like to reproduce this plot that is presented in McCaffrey's work. In it, the gas temperature is plotted against the height above the gas burner. The height is scaled in some fashion. We will talk about that later. Right now, the important part is we need to get different temperature readings at different heights above the gas burner. This means for the simulation, we need to position multiple devices along the center line at different heights above the gas burner. I've set up this case here, in which I have positioned multiple devices above the gas burner. The devices are simply labeled temperature 1, 2, 3, 4 up to 6. Again, reading in the _DEVC CSV file, and we get an overview over the different temperature readings. The first column again is the time, and the following columns contains the number of the individual devices. When plotting the data, we see now that there is some discrepancy. Even so I have positioned 6 different devices, I only see 3 different temperatures. Now the question arises, why is this happening? Let's have a look in SmokeView. We see here a line of devices in the center above the gas burner. When hitting G, SmokeView gives us an overview over the fluid grid. We can now hit Shift and 1 to align the view with one of the axes. If we then hit Alt and V, we get the isometric projection. With that we can have a look at the simulation domain exactly from the side. And it is obvious now that within a given cell, 2 devices are located. And this is why we see only 3 temperatures inside the plot. Let's have a look in Volume 1 of the Technical Reference Guide. In Chapter 2, an overview over the FDS model is provided. Specifically in Section 2.2.1, the staggered grid is explained. Here it tells us that different quantities are assigned to specific locations for a given gas phase cell. Figure 2.1 gives a visual representation. The takeaway message from this graphic is that scalar quantities, for example the gas phase temperature, the density or the pressure, are located at the cell center. Quantities like the velocities are located at the cell faces, while the vorticity is stored along the cell edges. The scalar quantities like temperatures are basically average values over the whole volume of a given cell. If we are locating multiple different point devices within a given gas cell, we will only be getting this average value. This is the reason why we see in this plot only 3 temperatures, because always 2 devices are falling inside one given cell. If you did find this video helpful so far, please consider to hit the like button. Even so, devices using the XYZ parameter can be located anywhere in the mesh. FDS will only give you valid data. It will not be interpolating between different locations. So then the question arises, what would happen if a device is located between cells? For example, you could set values that are locating the devices directly at a corner. What FDS does then is providing you information from the next valid cell. This valid cell is defined as the next cell in positive direction. I have set up a demonstration of this behavior here. In this situation, a single device is located at the center of 8 surrounding gas cells. Each of these surrounding gas cells also contains a temperature recording device. The device in the center is at a point where the corners of all the 8 surrounding cells meet. Now FDS should show for the center device the data recorded in the next positive cell. Let's have a look in the FDS input file. Here is the definition of the device that is located in the center. This is then followed up with a definition of the 4 devices that are located in the 4 cells below the center point. We can see this easily from the Z coordinates. Since the next valid cell is in the positive direction, we can already exclude the 4 lower cells. This next set here describes the definition of the 4 devices in the cells above the center point. We can already exclude the device labeled temperature 5, because its x and y coordinates are below the value of the center point. In the locations of the devices 6 and 7, there is also always a component that is lower than the position of the center point. So therefore 6 and 7 can be excluded as well. We are then left with the device temperature 8. For its position, all of the components are larger than the position of the center point. Now when we compare the data, we would expect that the temperature distribution shown from the center point is identical to the one that is recorded from temperature 8. I have read in the results of this demo simulation. We see here the individual temperatures from the center point and the 8 surrounding points. In this zoomed in plot, we can now see 8 distinct temperature distributions associated to each of the surrounding cells. The red line here at the bottom is associated to temperature 8. I expect now that when I'm plotting the temperature development from the center point, it should be drawn on top of this red line. Let's try it out. These black dots are representing this center temperature, which is, as expected, aligning with temperature 8. This is also the reason why I chose in the beginning the fluid cell resolution of 6 centimeters. Because remember, the edge length of the burner is 30 centimeters. With the fluid cell resolution of 6 centimeters, the edge length of 30 centimeters can be divided into 5 equidistant pieces. With that, I have a central column of cells right above the gas burner. We talk about how to choose a fluid cell resolution in more detail later on. In the center column, I can now position the temperature devices to record the temperature development over the center line. Now I would like to define the individual temperature devices at different heights above the gas burner. We can simply copy the input lines and give them different Z values. I decided to set up 14 different temperature devices. Since I'm a bit lazy, I have decided to set up a small script to write the input lines for me. In the script I provide a start value in meters for the first cell. There's also delta value in meters, this is the position of the next device, and then the number of devices needed. This is followed up with a string of the input lines for a device. I've introduced two placeholders here. One is used for labeling the device, the other one for setting the height. After printing all of them, they can be easily copied into the FDS input file. There's also convenience functions in FDS that can do this stuff for you. We will talk about this also later. Here in Smoke View we can now see the vertical distribution of the devices. After running the simulation, the temperature development can be plotted for each of the devices. The result would then look something like that. Yet to generate this plot we need to process the data further. This is also what we will be discussing later. For now, thank you very much for your time and have a nice day.